So the title of my talk is Alternating Sign Matrices and Hypermatrices. And I'm really going to tell you a bit of a story, if you will, okay? Some of the work that I'm going to report on here is done with my frequent collaborator, Geert Dahl from the University of Oslo, and also from a former student of mine, Mike Schroeder, now a collaborator. So that's basically the outline of my talk. I won't read it, but I'm going to talk about permutation matrices, a very common concept, alternating sign matrices, and alternating sign hypermatrices, and some stuff in between, okay? But first, okay, here are two orthogonal Latin squares of order 6. Okay, now you're thinking, of course, Terry, long time ago, proved that there don't exist orthogonal Latin squares of order 6, but I claim there are two orthogonal Latin squares of order 6, and you have to wait to the end of my talk in order to understand, okay, what this is all about, okay? So, permutations, as I say, is a very common concept. Everybody knows all about them. And I can identify a permutation with a permutation matrix. I treat them interchangeably. So for instance, the fact that there is a 2 in the 4th position here means that in the 4th row, there's a 2 in the 2nd column, okay? So these are fundamental objects in combinatorics and linear algebra and matrix theory, and you all know about them. Now, an inversion in a permutation matrix, or an inversion in a permutation, is simply a pair of integers such that a larger one precedes a smaller one, okay? Ik bigger than IL, even though k is less than L. And an inversion in terms of a permutation matrix really amounts to a 2x2 submatrix that looks like that matrix L2 there. And if you replace that submatrix with the 2x2 identity, you get a new permutation with fewer inversions, okay, if you do the switching there. So for example, there's the permutation 5, 4, 3, 2, 1. And if I do the inversion corresponding, or the inversion transformation there corresponding to that one and that one, you see that the number of inversions is actually decreased from the maximum for 5, which was 10, all the way down to 3, okay, like so. So I'll simply talk about that as an inversion-reducing transformation, okay, like so. But if the inversion takes place, okay, in a submatrix, which looks like that one you see there on the left, that is to say between the two ones, you have a 0 matrix, okay? If you do that inversion, okay, then the number of inversions is decreased by exactly 1, okay? Here's an example there, okay? If you look at that permutation there, in between the 8 and the 3, there are 3 numbers, and each is either less than 3 or bigger than 8, which really amounts to saying that that submatrix in between the corresponding ones is a 0 matrix. And if you do the inversion, the transformation, the interchange, the 8 and the 3, you get the one on the right there, okay? And you see that, well, I guess the number of inversions actually has been decreased by exactly 1, okay? Because what was worked for 8 will now work for 3, and what worked for 3 will now work for 8 there, okay? Like so. Okay, now in terms of permutations and inversions of permutations, there is a partial order, which is usually called the Brualdi order. It can also be called the Brualdi-Ehresmann order, okay? And we say that sigma is less than or equal to tau in the Brualdi order, provided sigma can be obtained from tau by a sequence of inversion-reducing transformations, okay? So in this partial order, the identity matrix is clearly the smallest permutation because it has no inversions whatsoever. And the anti-identity, n, n-1, n-2, all the way down to 1, is the maximum in this partial order because it has all possible n choose 2 inversions there, all right? So there's an example there of a permutation on the left, okay? I do the inversion-reducing transformation, okay? And I get the one on the right, and so I must have the one on the left is less than or equal to the one on the right in the Bruhat order. In particular, okay, if you have a partially ordered set, okay, you can talk about one thing being less than or equal to the other, and you could also talk about one covering or being covered by another. So in fact, sigma will be covered in the Bruhat order by tau, provided the number of inversions, okay, is decreased by exactly 1, which simply means all the inversions of sigma are inversions of tau, and tau has exactly 1 more inversion, okay? So the Bruhat order, okay, is a partial order, and it's graded, okay? You've got certain levels, and the levels are 0, the identity, no inversions, all the way up to n choose 2, the anti-identity, all possible inversions, and you have all these levels in between according to the number of inversions in the permutation. All right, so there is the Haase diagram of the Bruhat order of the permutations of order 3. You can see I've represented them both in terms of a permutation of 1 up to 3 and the corresponding permutation matrix. So you see, for instance, that this permutation is above, in fact, it's covered by that, because if you do this inversion reducing transformation, you end up with the thing on the right over there. So 2, 3, 1 covers 1, 3, 2, and that's the Haase diagram of the Bruhat order on S3. And of course, you can think of the Haase diagram, and I will later, as a graph, okay? As a graph, okay? All right. Now, there's another way to check the Bruhat order. Now, if I were to give you 2 permutations of 1 up to 100 and ask you whether one is less than or equal to the other in the Bruhat order, then according to what I've said before, you have to figure whether there's a sequence of inversion-reducing transformations that gets you from the one down to the other. Okay, that's our definition of the Bruhat order. But there is another way, I'll call it the sigma way, which is very computationally easy to check, okay? Namely, so start with any matrix whatsoever and define the matrix sigma of A, I'll call this sigma notation, okay, by simply adding up the ij entry of sigma of A is the sum of the entries in the leading I by j submatrix of A, okay? So there's an example there, and for instance, this 10 comes, well, it's in the 2, 3 position, so if I look at the 2, 3 over here, you can add up those entries, you get 4, 6, 7, 10. So that's where that 10 comes from. So with every matrix, in particular every permutation matrix, I can associate a sigma matrix, okay? And the big theorem is, big in the sense of computation, okay, that P will be less than or equal to Q in the Bruhat order, provided sigma of P entry-wise is bigger than or equal to sigma Q. So in order to check, all you have to do is compute this sigma matrix, that's no problem whatsoever, and then compare the corresponding n-squared entries, and if they always go one way, then you have the Bruhat order. If they don't always go one way, then the 2 permutations are unrelated in the Bruhat order, okay? So that's very simple to check there, okay? So for example, there's 2 permutation matrices P and Q. I can compute sigma P, take my word for it. I can compute sigma Q, take my word for it. And as you eyeball that, you see that every entry of sigma P is bigger than or equal to the corresponding entry of sigma Q. Okay, bigger than or equal, so P is less than or equal to Q in the Bruhat order. These are going in the opposite direction, okay? Keep that in mind, okay? Like so. If here's a second example there, let me just put the whole thing on there. There's P and there's Q. There's sigma P and there's sigma Q, okay? And if you look at this entry 1 bigger than 0, and if you look at this entry 1 less than 2, so these 2 have to be unrelated in the Bruhat order because it doesn't go in one direction always, okay? Like so. Now there's a very wonderful theorem, I think, of Mcneeley, okay, back in 1937, learned about this only 5 years ago, that says if you take, it works for infinite stuff as well, but let's take it, finite partially ordered set, then there is a unique minimal completion of that partially ordered set to a lattice. Minimal meaning the fewest elements that have to be added in order to make it into a lattice, okay? And it has to extend the original partial order. There's a unique minimal completion of any finite partially ordered set to a lattice, okay? Wonderful theorem of Mcneeley, 1937. It occurs in Birkhoff's book on lattice theory, the old book there. So as I say, if you have a favorite partially ordered set, if you're working on a partially ordered set, you can ask yourself, what is the Mcneeley completion of that partially ordered set, okay? The minimal lattice extending the original partial order, okay? All right, so let me recall for you here now the Bruhat order of S3, okay, there it is again, okay, just to remind you what that is. And you will notice, I think, that this is not a lattice, okay? Because if you look at these two elements, for instance, you ask, does it have a meet, okay? A unique element less than or equal to it, which is bigger than or equal to everything bigger than or equal to it, okay? It could be this or could be this, but it can't be both of them simultaneously. So this is not a lattice. These two elements don't have a meet. These two elements don't have a join in the lattice, okay? Like so. So one could ask now, what is the Mcneeley completion of this Bruhat order, okay? All right, so the question is, what are the new elements? We've got to take our partially ordered set, all right? It's not a lattice. We have to add elements to this partially ordered set in a way that extends the original partial order, and we want to do this in a minimal way, and there's exactly one way in order to do that, okay? So take that permutation there. You compute sigma p, you see it. You compute sigma q, you see it there, all right? And taking into account the entry-wise partial order, because remember, that's how the Bruhat order on the permutations can be defined in terms of entry-wise of sigma p and sigma q. So if you compute the maximum of the corresponding entries and the minimum of the corresponding entries, you see that they are right that. I'm going to go to the next slide so you don't have to remember that because I've repeated it up there, okay? So there's sigma min and sigma max, okay? And I ask, okay, is there a permutation whose sigma is sigma min? And is there a permutation whose sigma is sigma max, okay? It's no problem getting the max, okay? There's a permutation there, R, okay? And you could check quite easily, you can check it while I'm talking now, that gives you sigma r equals sigma max. But there is no permutation whose sigma is the sigma min, okay? Because if you have such a permutation, remember here's sigma min, and I'm looking for a permutation whose sigma is this, well I gotta have a zero, and then I gotta have a 1, and therefore this must be 0. And looking at this 0 here says there's got to be 2 zeros here, so I've got to have a 0 there, but then I've got to have a 1, okay? Here I've got, well, summing that up, I have a 1, okay, right there, okay? On the other hand, you look at this 1 here, and I know that when I take my permutation and I add up these 2 by 3, the entries in this 2 by 3, I got to end up with a 1, but I already have a 2. Okay, so clearly there's no permutation that's going to work there. On the other hand, if I put a -1 there, then all is okay and completed in the way that I have over there, okay? So in fact, there is something that's going to have to be in the Mcneeley completion of this partially ordered set, okay? The rest can be extended clearly in the obvious way there, okay? So what do I have there? I have there what is called, and I'll put this next slide there, an alternating sign matrix of order 3, okay? And an alternating sign matrix, well, maybe it's, well, I won't put it here yet, okay? An alternating sign matrix is a 0 plus or minus 1 matrix, so that if you look in any row or any column, and you look at the non-zero entries, forget about the zeros, it has to begin with a 1, alternate -1, -1, -1, and end with a 1. So the number of 1s in particular in any row or any column is 1 more than the number of -1s. It's got to go 1, -1, 1, -1, 1, ignoring the zeros, okay, like that, for both the rows and the columns. So that's an alternating sign matrix, okay? And this theorem of Lascaux and Schützenberzé, okay, says the following, okay? I'm going to come back to the alternating sign matrix, the second version. Here's what the Mcneeley completion is of the Bruhat order on the permutations of 1 up to n, okay? I'm going to describe it in terms of the sigma matrices, okay? That's sigma sub n there. They're all the non-negative integral matrices. Well, you can read what it says there. For each I, the entries in row I and column I are taken from 1 up to I, okay? Has to begin with a 0 or a 1, excuse me. I really don't need this mic for you to hear me, but, and end with a 1. I'm sorry, it has to end with an I. For each integer, the entries in row I and column I are non-decreasing, okay? They only go up. If you think of the sigma, it should go up, okay? And 2 consecutive entries in a row or column are either equal or there's an increase of 1. In particular, the last row and the last column are just the identity permutation, 1 up to n. And the lattice partial order is the entry-wise order. So that is the Mcneeley completion of the Bruhat order on the partially ordered set of permutations, okay? All right. All right, here's the second version, which I've already hinted at, okay? Namely, the Mcneeley completion is the set of n by n alternating sign matrices, okay? I've already described for you what they are, and the partial order on the alternating sign matrices is just an extension of the partial order on the permutations, because you have to add this kind of a matrix that really corresponds in terms of permutations to an inversion reducing transformation, okay, in such a way that all the intermediate matrices have to be alternating sign matrices. So you can get from one to the other, provided there's a sequence of adding things of this sort, staying within the class of alternating sign matrices, okay, to get this get the Mcneeley completion. So that's a wonderful theorem, 21 years old now, of Lascaux and Schützenberzé. This is the second version, sort of directly related to the permutations, because every permutation is an alternating sign matrix. There are no -1s. You don't have to worry about the alternating property. Every row begins with a 1 and ends with a 1. There's nothing else in between there, okay, like so. So the permutation matrices, as they would have to be here, are special cases of those. So let's talk about alternating sign matrices, okay? So here's an example of a non-permutation ASM, okay? You look at it there and you can mentally check it has the alternating property in each row, in each column. First non-zero is a 1, last non-zero is a 1, and it alternates 1, -1, 1, -1, 1, okay, like so. So there are ASMs. There are some, let me just put everything up here. There are some basic properties of ASMs, okay. The partial row sums, well, that's not too important there. So let me look at the second one there, that the ASM property, meaning if you look at the class of n by n ASMs and you subject them to the symmetries of the square, then you also will get another ASM. If you take an ASM, you could do that, you can do that, you can do this, you can do rotate, etc., and you always will end up with an ASM, because it's all very symmetric in terms of this definition there. So there's two examples of 6 by 6 ASMs. They actually have, this is even, the largest number of non-zeros that any alternating sign matrix can have. That we call the diamond ASM. In the even case, there are 2, because there's no middle row and middle column. In the odd case, there's actually 1, okay? And I'm sure you can imagine what that is. Okay. Now, very quickly, the bijection between the two versions of the Mcneeley completion, and let me just focus on the second bullet down there, that given a sigma matrix, you can find the corresponding alternating sign matrix, provided it has the right properties that we've talked about, okay, by defining Aij to be, well, you see it there, Xij plus Xi minus 1, J minus 1, minus two other entries there. So that's the way to go from sigma, okay, and I've described for you in terms of Laskos-Schütz-Berzé's theorem what the sigma matrices look like for the Mcneeley completion. And if you're given a sigma matrix, that's how you construct the corresponding alternating sign matrix. If you're given a sigma matrix of the type that we've talked about. All right. Let me just mention here, this lattice has some interesting properties. There's this notion of a bi-Grassmannian permutation, okay, which has one decrease, okay. A Grassmannian permutation has one instance where a bigger one precedes a smaller one as you go down. A bi-Grassmannian is something where which, I think I've said that right, where you have both that property for both the permutation and its inverse, okay? And if you see what happens here, these are all non-decreasing, and here's the switch from non-decreasing to, or maybe to whatever. You describe what that is, okay? From I have a 1 here to a 1 here, okay? So this 1 precedes that 1 over there. So the bi-Grassmannian permutations are those for which both it and its inverse have this property. And my student and I proved this about this partially ordered set, that the number of n by n ASMs at grade R, at level R in the Mcneeley completion, okay, is a polynomial in n of degree R, okay? We have some description of it, but nothing particularly nice. So the number at each level is a polynomial polynomial in n of degree equal to the level, like so, okay. Now, if you've never come across ASMs before, then you've never come across this remarkable theorem, okay? You can ask your combinatorialist, we know how many permutations of order n there are, n factorial. Well, how many ASMs are there, n by n ASMs? Well, there's a bit of a description there, 1, 2, 7. So look, that 7, okay, means there's exactly one alternating sign matrix of order 3 that's not a permutation matrix, because the 6 permutations work, so there's one more, okay? At order 4, they are equal to 42. And the celebrated theorem proved by Doron Zeilberger in 96, and another proof given by Greg Cooperberg also in 96, solving a conjecture of Mills, Robbins, and Rumsey, was, it's that obvious number, okay? That's the number of n by n ASMs. And I don't know how they first came about that conjecture, and I don't know how they first proved that conjecture, okay, like so. But it's obviously, it's not going to be a simple procedure in order to prove that that's the number of n by n ASMs. I gave a talk on alternating sign matrices in Pueblo, Mexico last summer, I think it was. And also there was Joel Spencer there, who is also a celebrated asymptotic person. And he wanted to know what that was asymptotically, and he told me that's what it is, okay? So it's about 1.3 to the n squared, are the number of ASMs of order n, as opposed to 3 to the n squared, which is the number of 0, 1, minus 1 matrices of order n, okay? Like so. He did this asymptotic analysis, and I haven't seen this in print. I'm not sure it will be, but I tend to quote this, okay. All right. Well, so here now is the Haase diagram for the 3 by 3 alternating sign matrices. Remember, I had a problem with these two permutations that didn't have a meet, and these two permutations that didn't have a join. Well, now there it is, okay? The unique non-permutation alternating sign matrix of order 3. That's the one, the new one, okay? And I won't say any more about that. If you want to know what this looks like for 4, there it is. And I won't describe the notation, okay? But there are 42 ASMs of order 4, and that's the Haase diagram of the Bruhat order on these alternating sign matrices there. I won't describe that. All right, so if you take that Haase diagram, as I mentioned, you could think of that as a graph, okay? And you could ask graph questions if you'd like, okay? Like so, okay? And in fact, there are really two graphs really that you should consider. The Haase diagram for the permutations, the Haase diagram for the alternating sign matrices with respect to the Bruhat order, okay, like so. All right, so if we look first at just the permutations, Bruhat order, you can talk about the down degree, everything joined to it below, which means how many things it covers, and you can talk about the up degree, how many things it is covered by, okay? The down degree and the up degree. And then you could talk about the total degree, which is the graph degree, the number covered by and the number covering, like so, all right? And if you define the maximum of the down degrees, the maximum of the up degrees, and the maximum of the total degree, okay, like so. And this was, first of all, it's easy to check D plus is D minus for the permutations, okay, because you can reverse the order of the integers there, okay. It was proved by Adin and Roykman in 2006 that this is the maximum down degree and therefore the maximum up degree, and this is the maximum total degree of any permutation in the Bruhat order on the permutations or permutation matrices. So basically I'm telling you it's known, it's been computed what these degrees are, okay, like so. All right, now suppose we now go to the alternating sign matrices and its Haase diagram relative to the Bruhat order, okay. Now you could look at just the permutations within the lattice of alternating sign matrices and ask for down degree, up degree, and total degree, etc. Okay. Well, we computed that. My student Mike Schroeder and I computed that. There as was, and it's also the plus. Okay, no problem. And the maximum total degree for the permutations within the partial order, within the lattice of alternating sign matrices. It doesn't matter what they are at the moment, it's just, I'm just telling you that they've been computed, okay? And now you could go and look at the full lattice alternating sign matrices, and let me put it all there, all right? And what I'm basically telling you, and I'm not even going to read this, okay, is that we computed the maximum down degree, therefore the maximum up degree, okay, and we computed the maximum total degree. So what this is saying, for instance, in the odd case, this is the maximum degree of the graph. In the even case, this is the maximum degree of the graph, okay? And we know exactly when equality occurs there, okay, like so. So again, I don't especially think you want to take in what the values are, but just that we have done that, okay, like so. Let me just, I was going to maybe skip this, but I'm going to do it quickly, okay? Sorry, it'll be quick, okay? Origins of ASMs. If you've never saw ASMs before, then you probably don't know how they originate. Well, how would you, okay? And they originated by using the Dodgson's condensation formula for determinants and extending that to a sort of general case here, okay? So there is the lambda determinant for a 2x2 matrix there. Rather than the -1 that you would have there for the determinant, I put in a lambda, okay? And if you use Dodgson's formula, condensation formula, but using the lambda, what you end up with is that. I'll just describe what it says there. It basically, Dodgson's condensation formula gets you down to the determinants of 2 by 2 matrices, okay, like so. And the description is, you take the lambda determinant of the n minus 1 by n minus 1 matrix in the, well, think of it as you've got an n minus 1 by n minus 1 in the upper left, I guess. You got an n minus 1 by n minus 1 in the lower left. And you have n minus 1 by n minus 1 in that corner, and n minus 1 by n minus 1 in that corner, okay? Think of that as a 2 by 2 matrix, okay, like so. And take the determinants there, okay? This would be minus 1 if it were Dodgson's formula, but I'm going to put in a lambda there. And then you have to divide by the determinant of that n minus 2 by n minus 2 in the middle. Okay, like so. And if you iterate this, you'll reduce everything to 2 by 2 matrices, okay? So that's Dodgson's condensation formula. And what Mills and Rumsey, etc., did was to apply it to the lambda determinant, okay? So let me quickly, I don't want to spend a lot of time on there. So there's the lambda determinant of a 3 by 3 matrix, okay? And you notice that if lambda is minus 1, this term goes out, and all the other terms are right sign corresponding to the corresponding permutation. For instance, this is 3, 1, 2, okay? And that is a even permutation, I hope, okay? Yeah, 2 inversions, 3, 1, 3, 2, okay? So there are 7 terms there. That should ring a bell to you already, okay? 6 of them correspond to the permutations of order 3. And this strange looking one over here, whoops, sorry, corresponds to an alternating sign matrix. What is the alternating sign matrix? Look at the exponents and put them in the corresponding position. A minus 1 in the 2, 2 position. A 0 in the A1, 1 position, because there's no A1 there. And what you end up with is the unique alternating sign matrix of order 3. Okay? All right. So that's the lambda determinant of the 3 by 3. Okay? There's exactly one term corresponding to an alternating sign matrix. There you see it. All right? And in general, that's the lambda determinant. It's a summation over all the alternating sign matrices of order n. Okay? As indicated there, just like that term there, with a certain polynomial in lambda in front of them. So rather than in the determinant where we sum over all permutations of order n, here we're going to sum over all the Mcneeley completion under the partial order of the permutations, okay? That's the lambda determinant. The number of terms is the number of n by n alternating sign matrices. All right, so I have to get to my punchline. Alternating sign hypermatrices. Well, hypermatrices like hypergraphs, like tensors, like multidimensional matrices, okay, are quite in vogue these days. Many people are looking at those, okay? So what do I mean by a hypermatrix? Well, 3 dimensions, that's okay. It's got row lines, it's got column lines, and it's got vertical lines, right? There are 3 kinds of lines. And it's got row planes, these kind of planes, I'm not sure, it doesn't matter what I name them, and these kind of planes, okay? 3 kinds of planes, that's all you need to know. You don't have to worry so much about the notation there, okay? So that's what a n by n by n hypermatrix looks like, okay? And the notation I'll use is simply first level A1 below, or A2 below A3, etc., below A1. Or I could describe it like that, or I could describe it like this, and I have one other way, which I'm not sure which it is, okay? But you understand, okay? So that northeast arrow is read as AI is below AI plus 1 in the hypermatrix, or AI plus 1 is on top of AI, okay? Like so. All right, so here is what we call an alternating sign hypermatrix, ASHM. It's simply a 0 plus or minus 1, n by n by n, so that it has the alternating property in the lines in all possible directions. Okay, there are lots of lines, okay? In fact, how many are there? I guess 3n squared, right? You have n squared in each direction there, okay? And special case of this is the permutation hypermatrix with exactly 1, 1, 0, 1, exactly 1, 1 in each line. Those are the alternating sign hypermatrices not having any ones, any minus ones. So these are three-dimensional generalizations of what sometimes are called permutation matrices, these permutation hypermatrices. All right, so here's an example, okay? There's my nice 3 by 3 alternating sign matrix, and you could check that is a alternating sign hypermatrix of order 3, okay? The middle plane section, in fact, no matter which way you look at it, is going to be that unique 3 by 3 alternating sign matrix there, okay? Here's another example, which is sort of the generalization of the diamond ASM to the diamond ASHM, okay? Looking like as you see there, okay? I'm not going to describe that other than to say, well, there's a nice alternating sign hypermatrix of order 5, which can be generalized. And in fact, this generalization, in particular this case for n equal to 5, it has the largest number of non-zeros in any n by n by n alternating sign hypermatrix. In fact, not only that, but at each level, you have the maximum possible that you could have in such a alternating sign hypermatrix. All right, I already said that there, basically, what I've just said in verbally here about the extremal properties of these type of alternating sign hypermatrices. Okay, we're getting near the punchline, okay? Alternating sign hypermatrix Latin squares, okay? All right, so I got to explain what I started my talk with, okay? Well, first of all, let me remind you about Latin squares, okay? Because I want to generalize some of these properties. As we know, a Latin square is really equivalent to a n by n by n permutation hypermatrix, okay? Equivalent to that. So for instance, if I take that Latin square and I look at where the 1s are, put them at the lower level. I look at where the 2s are, put them at the second level. Look where the 3s are, put them at the third level. I get a permutation hypermatrix. And this is reversible. If you start with one of those, you can construct the corresponding Latin square. Equivalently, what this amounts to is taking a one factorization of the complete bipartite graph KNN, which is equivalent to taking the all ones matrix and writing it as the sum of n permutation matrices. And then you get the corresponding Latin square by simply taking 1 times P1, remember this up here, 2 times P2, 3 times P3, etc. Okay? So those are Latin squares. You can think of it as a n by n made up of the integers 1 up to n with no repeat in a row or a column. Or you can think of it as a permutation hypermatrix of order n. Okay, like so. All right, so how should we define an alternating sign hypermatrix Latin square? I have to tell you, I was very excited when it came up with this idea. And maybe it's, well, you can react to it as you wish, okay? But I was pretty excited about this, okay? Like so. So replace the permutation ASM hypermatrices with any alternating sign hypermatrix. Remember, the permutation hypermatrices are special alternating sign hypermatrices. So what do I mean by that? The following. If you take a n by n by n alternating sign hypermatrix, here it is, and you add up the entries, say, in each of the vertical lines, what are you going to get? 1, minus 1, 1, minus 1, 1. You're always going to get 1. You're going to get J sub n because of the alternating property beginning and ending with a 1. All right, so if you take such an alternating sign hypermatrix, I think I'm going beyond where I'm supposed to go here, it gives you a decomposition. And mimicking what we did for Latin squares, define an ASHM Latin square to take 1 times A1 plus 2 times A2 Rather than permutations, 3 times A3 all the way up to n times AN. Okay, like so, all right? So, n by n alternating sign hypermatrices, in fact, you can regard as generalizations of Latin squares there. All right, here's an example, okay? So there's the 4 by 4 by 4 diamond alternating sign hypermatrix. And if you do what I've said to do, 1 times this plus 2 times that plus 3 times that plus 4 times that, that's what you get. So there is a 4 by 4 alternating sign hypermatrix Latin square. I think those are the words I'm using there. Okay. All right. Here are some, very quickly, I won't, oh, I still have some time. The set of entries is always 1 up to n. You can prove that, okay? And you could also prove, and I'm not going to say much about this, some properties about these entries here, okay? I don't expect you to take that in, okay? But I want you to note that it's always 1 up to n, okay? So you have a non-negative integral matrix, the entries 1, 2, up to n, okay? Like so. Now, there's another view of alternating sign hypermatrix Latin squares that I'd like to describe here, okay? Just like a Latin square, okay, we can regard a alternating sign hypermatrix Latin square as a 0, 1 hypermatrix. If you look where remember the entries are only 1 up to n, so you look where the 1s are, put in 1s in those positions. You look where the 2s are, put in the 2s in those positions. You look where the 3s are, put in the 3s in those positions, etc. Okay, like so, all right? So in fact, what you get is a decomposition of Jn into n by n 0, 1 matrices, just as you do for the case of ordinary Latin squares there, okay, like so. So we have 2 ways, in fact, to look at these alternating sign hypermatrices in these decompositions. One is by adding up the alternating sign matrices. The other is by adding up these 0, 1 matrices that in both cases they give you Jn. Okay, so I don't remember what's on here, but let me just, here are some properties of these things. You will get an you will get an ordinary Latin square exactly when, okay, those alternating sign matrices are permutation matrices, okay? That's the only time that you get it. You have to have a permutation ASHM, and you will get a Latin square. Each row and column is actually majorized, this is the dominance order, by the, well, the vector n minus 1, 2, up to 1. If you don't know what majorization is, or the dominance order, don't have to worry about that, okay? But we don't know, okay, how many times an integer may be repeated in an n by n alternating sign hypermatrix Latin square. We have examples where you get 2n of some entry. We don't know, well, we think that might be the maximum, but we really don't know. And the second question here concerns that majorization there, okay? Whether or not you can get any vector that's majorized by this n minus 1, 1 by this property here. Does there exist an n by n ASM so that you end up with that when you multiply by n minus 1, n minus 2, etc. Okay, oh, I got to do this. This is where I'm going to explain. All right. Now, you know what it means for 2 Latin squares to be orthogonal, right? All right. If you think of a Latin square in terms of 1 times the permutation plus 2 times the permutation plus n times the permutation, okay, then we know that the sum of those p's is j, the sum of the q's is j, and orthogonality means, okay, in terms of the ordinary inner product, that pi qj equals 1 when you take their, you know, you multiply corresponding entries and you add them up. There's got to be just a 1 there in order that everything occur exactly once, okay? All right. So now you can generalize this to alternating sign hypermatrix Latin squares, okay? After all, it's written as 1A1 plus 2A2 plus NAN, where these are alternating sign matrices rather than permutation matrices. Similarly over here. So we can define them to be orthogonal provided that dot product is equal to 1 whenever you take an AI here and a BJ here, which corresponds to whenever you take a PI here and a QJ here, the dot product is equal to 1. Okay? All right. So we had I'm talking about a paper that's been submitted, okay, now. And we had a question in this paper about, does there exist a pair of orthogonal, well, here it is, 6 by 6 alternating sign hypermate? We didn't know. We should have computed this, try it, but we didn't. This paper was posted on the archive. And Eric Egge, maybe some of you know Eric Egge from Minnesota, okay, took the paper, did some computation, and you know what the next slide is, okay? It's those two orthogonal alternating sign hypermatrix Latin squares, okay? Like so. So Terry didn't have a wide enough class, okay? He had to look at the alternating sign. I mean, it just missed one, okay? But that's it. So let me just conclude with some references there in case any of you are interested in. This is a paper, I've talked a bit of, I haven't talked so much about this, that just appeared in the Advances in Applied Mathematics, okay? This is the paper where we discuss the Latin square stuff, and this has been submitted. This is my first paper on this type of stuff where I wasn't aware enough of what was going on here. This is a paper that my student Mike and I, that was just published in Discrete Math in this year, okay? If you want to know more about lambda determinants and the alternating sign hypermatrix conjecture, here's a beautiful book to look at, okay, by David Bressoud. There's the Cooperberg paper I mentioned. There's Lascaux, Schützenberzé. There's a nice little paper by Madhyar in Algebraic Combinatorics dealing with the Bruhat order, but trying to look at complete flats in n-dimensional vector space. They're related to this Bruhat order. There's Mills, Robson, and Rumsey. There's this wonderful theorem of Mcneeley partially ordered sets. Jessica Stryker talked about the alternating sign matrix polytope it was her thesis actually, published in the Electronic Journal of Combinatorics in 2009. And then there's Doran Zeilberger's proof. And I thank you so much for your attention.
Thank you, Richard. Any questions that you would like to? Right, I have a small question. When you were writing J sub n as the sum, and then you had the other one, the following line, it reminded me of distance regular graphs and a basis, and the basis in terms of distance matrices and in terms of power matrices. And I wondered whether these could be changed to a graph somehow. You know.
Have your next research.
Okay, okay.
I want to mention just, well, you always ask a question like me.
Thank you. It seems like you have or potentially have two definitions of alternating sign hypermatrix Latin squares, because traditionally with the Latin squares you just have symbols. You don't necessarily make the symbols to be the positive integers. Well, maybe it does. So have you seen what happens if you actually just keep them as undefined symbols?
I don't know the answer to that question. Somehow I think that the properties of Latin squares that are known are really independent of what you call the entries of the matrix, okay, whether you call them 1 up to n or x1 up to xn, although maybe by calling them indeterminates you can do something with them. The one thing I wanted to mention, I defined an alternating sign hypermatrix so that in each of the lines, okay, you have alternating. So that means alternating sign matrix, alternating sign matrix, all these directions, alternating sign matrix in all these directions. Now, of course, you can look at just alternating sign matrix in one direction like that. Then you don't necessarily get the entries are 1 up to n. You could have entries beyond 1 up to n, okay? And, of course, if you take one of these, as I call them, alternating sign hypermatrices, well, you know, you could look at them in either three directions in order to get a alternating sign hypermatrix Latin square. I just looked at it in one direction, okay? But there's two other directions that you can look at, and you get three things, and what the relationship between those three things are, I don't know. I mean, I think I could spend the rest of my mathematical life dealing with alternating sign matrices and hypermatrices, and maybe I won't do it everything, but I certainly am spending some time on it again. Thank you again.
Any more questions? Right, so we thank the speaker again.